Beyond physical memory policies, in a virtual memory manager, life is easy when you have a lot of free memory. A page fault occurs, you find a free page on the free page list and assign it to the faulting page. Unfortunately, things gets a little more interesting when little memory is free. In such case, this memory pressure forces the OS to start paging out pages to make room for actively used pages. Deciding which page or pages to evict is encapsulated within the replacement policy of the OS. Historically, it was one of the most important decisions the early virtual memory systems made, as older systems had little physical memory. So, because of the small memory, kicking out uh, inaccurate pages will lead to this disastrous event, uh, even more before. But as we will later learn that change a bit and then change again. So because the cost of transferring to the disk is tremendously low, uh, we don't allow that kind of replacement. But it changed again with the introduction of SSDs. The crux: how to decide which page to evict. How can the OS decide which page or pages to evict from memory? This decision is made by the replacement policy of the system, which usually follows some general principles discussed below, but also includes certain tweaks to avoid corner case behaviors. So these are the basics, or where this replacement came from. It's just an interesting topic to learn from because it also tackles about algorithms, kind of like the scheduling part. So we will discuss this. Cache management. So to understand this, we need to understand cache management. Given that main memory holds some subset of all the pages in the system, it can rightly be viewed as a cache for virtual memory pages in the system. Thus, our goal is picking a replacement policy for this cache to minimize the number of cache misses, i.e., to minimize the number of times that we have to fetch a page from disk. Knowing the number of cache hits and misses, let us calculate the average memory access time, AMAT, for a program. A metric computer architects compute to for hardware caches. Specifically, given these values, we can compute the AMAT of a program as follows. AMAT equals TM plus PMIS times TD, where TM represent the cost of accessing memory, TD is the cost of accessing disk, and PMIS the probability of not finding the data in the cache, a miss. So TM represents the cost of accessing memory. So there's always a cost of accessing memory, but it's a greater cost to access the disk. PMIS is the probability of not finding the data in the cache. So how likely are you not to find the data you require in the cache? Therefore, slow down the system. PMIS varies from 0.0 to 1.0, and sometimes we refer to a percent miss rate instead of a probability. Like 10% miss rate means PMIS equals 0.10. Note, you always pay the cost of accessing the data in memory. When you miss, however, you must additionally pay the cost of fetching the data from the disk. So these are the basics on how we will create or determine the replacement algorithm. For example, let us imagine a machine with a tiny address space, 4 kilobytes with 256 byte pages. Thus, a virtual address has two components, a 4-bit VPN, the most significant bits, and an 8-bit offset, the least significant bits. Thus, a process in this example can access 24 or 16 total virtual pages. In this example, the process generates the following memory references, like virtual addresses 0x000, 0x100, 0x200, 0x300, 0x400, 0x500, 0x600 to 0x900. These virtual addresses refers to the first byte of each of the first 10 pages of the address space, the page number being the first hex digital of each virtual address. Let us further assume that every page except virtual page 3 is already in memory. Thus, our sequence of memory references will encounter the following behavior: hit, 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 miss, hit, 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 hit. We can compute the hit rate, the percent of references found in memory. 90%, as 9 out of 10 references are in memory. The miss rate is thus 10%. P miss equals 0.10. In general, P hit plus P miss equal 1.0. Hit rate plus miss rate sum is 100%. To calculate AMAT, we need to know the cost of accessing memory and the cost of accessing disk. Assuming accessing memory TM is around 100 nanoseconds and the cost of accessing disk is about 10 milliseconds, we have the following AMAT: 100 ms plus 0.1 times 10 ms, which is 100 ms plus 1 ms, or 1.0001 ms, or about 1 millisecond. If our hit rate had been instead been 99.9%, P miss equals 0.001, the result is quite different. AMAT is 10.1 microseconds, or roughly 100 times faster. As the hit rate approaches 100%, AMAT approaches 100 nanoseconds. Unfortunately, as you can see in this example, the cost of accessing disk is so high in modern systems that even a tiny miss rate will quickly dominate the overall AMAT of running programs. Clearly, we need to avoid as many misses as possible or run slowly at the rate of the disk. So this is the reason why we the motivation for creating this replacement algorithm is because this slow transfer leads to enormous problems. The optimal replacement policy. To better understand how replacement policy works, we need to get the idea from DSA, in which we imagine the best possible case. So, since we're creating an algorithm, the best possible or the best imaginable big O is still useful here. The optimal replacement policy leads to the fewest number of misses overall. Belady showed that a simple but unfortunately difficult to implement approach that replaces the pages that will be accessed furthest in the future is the optimal policy, resulting in the fewest possible cache misses. So the furthest out from now policy, which I described in the previous video, still applicable here because it's just reduced the fewest possible cache misses. So that's the idea behind it, and at the same time we will gonna use the hardware characteristics to run around or to work with the realistic limitation of our hardware or the science of our hardware later, because as we will later see, the temporal and spatial locality plays a lot on determining what algorithm to use. Tip: comparing against optimal is useful. Although optimal is not very practical as a real policy, it is incredibly useful as a comparison point in simulation or other studies. Saying that your fancy new algorithm has 80% hit rate isn't meaningful in isolation. Saying that optimal achieves an 82% hit rate and thus your new approach is quite close to optimal makes the result more meaningful and gives it context. So if you have this optimal, you have that baseline, so you automatically you reduce the cognitive load of thinking about it all the time. At the same time, you're hitting a target that is known realistically. So approaching something or some percentage near to that makes it more meaningful and gives it context, which helps you understand it better. So it's kind of like in design, where representation or a different representation sorry about that. I just have to uh, talk to the trash. I don't know what's the English of that. Trash person or garbage person. Yeah. So yeah. So let's go back. So it's like in design, a different representation for us humans allow us to make context. Kind of like an idioms or a different interface allow us to better understand it. To capitalize with our strength as well, with our hardware, with our visual and hearing brain. Let's assume a program accesses a following stream of virtual pages. In the figure, you can see the following actions. Not surprisingly, the first three accesses are misses, as the cache begins in an empty state. Such a miss is sometimes referred to as cold start miss or compulsory miss, because obviously the first access will not be part of TLB. Let's say you start opening your laptop or computer. Then we refer again to page 0 and 1, which both hit in the cache. Finally, we reach another miss to page 3, but this time the cache is full. A replacement must take place, which begs the question, which page should we replace? With the optimal policy, we examine the future of for each page currently in the cache 0, 1, and 2, and see that 0 is accessed almost immediately, 1 is accessed a little later, and 2 is accessed furthest in the future, so we evict the 2. Thus, the optimal policy has an easy choice, evict 2, resulting in page 0, 1, and 3 in the cache. So this is just the optimal policy. But we will still have to work on the limitation of our system. The next three references are hits, but then we get to page 2, which we evicted long ago, and suffer another miss. Here, the optimal policy again examines the future for each page in the cache, 0, 1, and 3, and sees that as long as it doesn't evict page 1, which is about to be accessed, will be okay. So here, we evict 3, but as long as we doesn't evict 1, will be okay because that's the most recently accessed. So 031, we can also evict 0. But for this purpose, so the example shows page 3 getting evicted, although 0 would have been a fine choice too. Finally, we hit on page 1 and the trace completes. So since these are the access pattern until 1, we get this hit percentage. So we can also calculate the hit rate for the cache. With 6 hits and 5 misses, the hit rate is hits over hits plus misses, which is 6 over 6 plus 5, or 54.5%. So this will gonna be our baseline. So we will gonna try to create to see the algorithm that will approach close to this, because again we need to work with the hardware and different edge cases. You can also compute the hit rate modulo compulsory misses. Ignore the first miss to a given page, resulting in a page 85.7% hit rate. Unfortunately, as we saw before in the development of scheduling policies, the future is not generally known. You can build the optimal policy for general purpose operating system. Thus, in developing a real deployable policy, we will focus on approaches that find some other way to decide which page to evict. The optimal policy will thus only serve as a comparison point to know how close we are to perfect. So because the future is inherently uncertain, we need to make intelligent guesses, kind of like the scheduling policy we had before. We have to learn from the history. But speaking of history, before we provide those, many early systems avoided the complexity of trying to approach optimal and employed FIFO. So a simple policy, which is FIFO. FIFO has one great strength. It is quite simple to implement. Comparing FIFO to optimal, FIFO does not notably worse at 36.4% compared to 54.5%. or 57.1% excluding compulsory misses compared to 85.7%. FIFO simply can't determine the importance of blocks even though page 0 had been accessed a number of times. So since it doesn't learn from the past, it doesn't have state, it still evict it even though it doesn't make sense. So that's the weakness of FIFO. It's not that smart. FIFO still kicks it out simply because it was the first one brought into memory. So these are the example. First in, miss. So it still encountered the miss from the early pass through, and then hit, and then since that we evict the 0, so we get the miss. We evict the 0 simply because that's the first first page we access. Aside Bilides anomaly, so Bilidi of the optimal policy and colleagues found an interesting reference stream that behave a little unexpectedly. The memory reference stream 1234, 125, 12345. The replacement policy they were studying was FIFO. The interesting part, how the cache hit rate change when moving from a cache size of 3 to 4 pages. In general, you would expect the cache hit rate to increase, get better, when the cache gets larger. So because a larger cache, or kind of like a larger page, or a large, a larger cache in TLB in a CPU, you would expect that FIFO would work better. But in this case, with FIFO, it gets worse. Calculate the hits and misses yourself and see. This odd behavior is generally referred to as Bilady's anomaly, to the charging of his co-authors. Some other policies, such as LRU, don't suffer from this problem. Can you guess why? As it turns out, LRU has what is known as a stock property. For algorithms with this property, a cache of size n plus 1 naturally includes the contents of cache of size n. Thus, when increasing the cache size, hit rate will either stay the same or improve. It cannot decrease, or it cannot unimprove, if there's that word. FIFO and random, among others, clearly do not obey the stock property and thus are susceptible to anomalous behavior. So remember the stock, guys, we discussed in previous videos in DSA algorithm. So stock basically is a form of algorithms and data structures that allow us to optimize operations compared to other algorithms. Recommend you going back with it. So it's a last in first out principle. So this means that the last element added to the stock is the first one to be removed. So the stock is kind of like the undo. So that also relates to this, to the LRU, which is the algorithm we will base our most useful algorithm when it comes to this replacement fallacy. On the other hand, which we will later discuss, is the behavior of this algorithm, like the first in first out compared to random and then last in first out. I mean, this LRU is not just last in first out, but it has that property, so that there is an advantage on using that to this to a larger cache. But for loop, like for looping or accessing the same page over and over again, random works better. But you rarely do that in real system, kind of like accessing the same page of memory. So it really depends on your goals, just like we discussed in data structure and algorithm. No one fits all, right? Another simple policy, random. So after that, they created this random policy. Another similar replacement policy is random, which simply picks a random page to replace under memory pressure. So all of this replacement policy works under memory pressure, right? Because we will only use the LW and HW parameter if we want to keep some space. But a lot of times that there's some you need to for small memory constraint or for small hardware constraints, you can do this. You can remove or you can use a better replacement policy. So going back, a random has properties similar to FIFO. It's simple to implement, but it doesn't really try to be too intelligent in picking which blocks to evict. In the example above, random does a little better than FIFO and a little worse than optimal. So as you can see, this is the usefulness of the optimal. So the random works better than FIFO, but less so with optimal. In fact, we can run the random experiment thousands of times and determine how it does in general. Figure 22.4 shows how many hits random achieves over 10,000 trials, each with a different random seed. As you can see, sometimes just over 40% of the time. Random is as good as optimal, achieving 6 hits on the example trees. Sometimes it does much worse, achieving 2 hits or fewer. So evic 0, 1, 3. Random performance over 10,000 trials. So frequency and then number of hits. Using LRU, FIFO kicks out the page. Let me just expand on this. So these are the number of hits as we move with frequency. So the on this right part, or as the number of hits increases, the frequency also increases. So that's kind of like the properties you can observe in this, or conclusions we can observe on that behavior. Using history, LRU. So this is where we will include the state and the LRU we've been discussing even with the previous video. FIFO kicks out the page that was first brought in. If this happens to be a page with important code or data structures upon it, it gets thrown out anyhow, even though it will soon be paged back in. Thus, FIFO, random, and similar policies are not likely to approach optimal. Something smarter is needed. If a program has accessed a page in the near past, it is likely to access it again in the future. One type of historical information a page replacement policy could use is frequency. So again, because of this memory pressure to replace code, and at the same time needs to be smart to not replace a page with important code or data structure upon it, we will use a page that has been accessed in the near past or most recently used. We call that MRU, because it will likely be accessed it again in the future. One type of historical information a page replacement policy could use is frequency. So if a page has been accessed many times, perhaps it should not be replaced as it clearly has some value. So another property or criteria is frequency. If you have accessed it many times, you will likely access it again, because another thing with our psychology is we're a creature of habit, just like in about face design. We only use few functions. Kind of like this in OneNote, I only use few functions like the copy and paste of screenshots, and then copy and paste of paragraphs, and that's about it. And then just organizing my notes. So like the keys of up and downward keys in my keyboard, Control C, Control Z, Control Y, those are the keys that's most useful to me. So I likely will access that again. So LRU use that. So that's how the modern virtual memory of our operating system works. A more commonly used property of a page is its recency of access. The more recently a page has been accessed, perhaps the more likely it will be accessed again. But again, we cannot predict the future, because it's incredibly complex. So we can learn from the future, we can approach the optimal, but we can never be perfect in predicting the future, right? We can prepare for a worst case scenario, and we can learn from the past, such as like scheduling policy from our CPU, which did a really good job in managing the hardware and its constraints, which is the processor. This family of policies is based on what people refer to as the principle of locality. So we discussed that in the previous video as well. which basically is just an observation about programs and their behavior. What this principle says quite simply is that program tends to access certain code sequences in a loop and data structures. So code sequences, that is a loop usually, and a data structure, which is usually an array accessed by the loop quite frequently. We should thus try to use history to figure out which pages are important and keep those pages in memory when it comes to eviction page. So we need to determine, or those locality are the observation among this hardware. Of course, like, we cannot predict the future, but these tend to exist in this hardware. So those code sequences, which is loops, and data structure, which is array accessed by those loops, tend to be accessed again because it is accessed frequently. And also, we are a creature of habit. So we should thus try to use history to figure out which pages are important and keep those pages in memory when it comes to eviction time. So we will use that metadata, or that knowledge, to avoid kicking those important pages out. And thus, a family of simple historically based algorithms are born. So this first, the least frequently used policy replaces the least frequently used page when an eviction must take place. Similarly, the least recently used policy replaces the least recently used page. So these are different policies, but it takes advantage of frequency and recency knowledge. These algorithms are easy to remember. Once you know the name, you exactly know what it does, which is an excellent property for a name. The figure 22.5, page 7, shows the result of the figure. You can see how the LRU can use history to do better than stateless policies, which has no state, such as random FIFO and random or FIFO. In the example, LRU evicts page 2 when it first has to replace a page, because 0 and 1 have been accessed more recently and frequently. And then, so if you can't find the frequent, you can find the recent, right? That's that's also the what do you call that? The reasoning we had with our optimal policy earlier. It then replaces pages 0 because 1 and 3 have been accessed more recently. In both cases, LRU's decision based on history turns out to be correct, and the next references are thus hits. MFU, or most frequently used and most recently used, on the other hand, do not work well. Most frequently used and MRU, or most recently used, do not work well because they are the opposite of least frequently used and least recently used, as they ignore the basic or the locality most program exhibits instead of embracing it. So aside types of locality, there are two types of locality that programs tend to exhibit. The first is known as spatial locality, which states that if a page P is accessed, it is likely the pages around it, says P minus 1 or P plus 1, will also likely be accessed. The second is temporal locality, which states that pages that have been accessed in the near past are likely to be accessed again in the near future. So as you notice, the only concept it incorporates here, or previous that we have discussed, is the recent locality. So where is the frequent? Because this spatial locality obviously about the position of the page in the actual memory. So the assumption of the presence of these types of locality plays a large role in the caching hierarchies of hardware systems. So because there's an assumption of this that tends to happen, because again humans tend to access uh, near data near them, or the most recent and most frequently accessed. There's an assumption which deploy many levels of instruction data and address translation caching to help programs run fast when such locality exists. So it also determine the design of caching hierarchies of hardware and software. Of course, the principle of locality, as it is often called, is no hard and fast rule that all programs must obey. Indeed, some program access memory or disk in rather random fashion and don't exhibit much or any locality in their access streams. Thus, while locality is a good thing to keep in mind while designing caches of any kind, hardware or software, it does not guarantee success. Again, because we cannot predict the future. Rather, it's heuristic that often proves useful in the design of computer systems. So heuristics, kind of like the second level of model. So when we have heuristics, we know that we have those known rules, kind of like the efficiency, effectivity, easy to learn, easy to remember, safe principles or heuristics of interaction design. So it's just a heuristics, but it could be proven false in some circumstances. So there's no hard rule or science behind that. I mean, it's a exact science. It's an observation that tend to happen. So, but it cannot be proven, right? So, but we have defined that it's a heuristic. So that's the science of that. So, how do we implement this? How can we work on this in production? So, how can we actually deploy that in production? Because it's one thing to know these theories exist, that this optimization actually makes our systems better in this unknown future. How do we do that? Before we do that, we need to understand the workload examples. So a real workload examples. First, here we'll examine more complex workloads instead of small traces. However, even these workloads are greatly simplified. A better study would include application traces. Our first workload has no locality, which means that each reference is to a random page within the set of access pages. So let's imagine a set of access pages that is accessed randomly. In this simple example, the workload accesses 100 unique pages over time. Choosing the next page to refer to at random, overall 10,000 pages are accessed. In the experiment, we vary the cache size from very small, 1 page, to enough to hold all the unique pages, 100 pages, in order to see how each policy behaves over the range of cache sizes. So since we cannot just test it in one go, we need to test it over time, kind of like how we resolve or create the multi-level feedback queue. We didn't resolve that in just one interval, but rather in a long interval and learn from history. So here we can draw a number of conclusions from the graph. First, when there is no locality in the workload, it doesn't matter much which realistic policy you are using. LRU, FIFO, and random all perform the same, which with the hit rate exactly determined by the size of the cache. Second, when the cache is large enough to feed the entire workload, it also doesn't matter which policy you use. All policies, even random, converge to 100% hit rate where all the reference blocks fit in cache. Finally, you can see that optimal performs noticeably better than realistic policies, peeking into the future. If it were possible, does a much better job replacement. So here, our optimal policy in no locality workload works better than all of the introduced approach, LRU, FIFO, and random. So the next workload we examine is the 80-20 workload, which exhibits locality. So here's where our LRU shine. 80% of the references are made to 20% of the pages, the hat pages. So this is the Pareto principle, which exists everywhere, like we discussed in the previous video as well. The remaining 20% of the references are made to the remaining 80% of the page, the cold pages. In our workload, there are total 100 unique pages. Thus, hot pages are referred to most of the time, and cold pages the remainder. Figure 22.7, page 10, shows how the policies perform with this workload. So as you can see, LRU does better than RAND and FIFO, and it is approaching the optimal workload. So how do we get that with all of the edge cases we want to protect? So you might be wondering, is LRU's improvement over random and FIFO really that big of a deal? The answer, as usual, is it depends. If each miss is very costly, not uncommon, then even a small increase in hit rate, reduction in miss rate can make a huge difference on performance. So let's say like you're running out of memory, and some pages that you kick out are really that big deal on the system, such as system display. So yes, this situation requires you, or LRU is important. If misses are not so costly, then of course the benefits possible with LRU are not nearly as important. Then we go back to the argument of whether we really need, or we really need this replacement policy, or we must avoid it in the first place. So let's look at one final workload. We call this one the looping sequential workload. As in it, we refer to 50 pages in sequence, starting at 0, then 1, up to page 49. So this is the looping I was talking about. And then we loop, repeating those access for a total of 10,000 access to 50 unique pages. The last graph in figure 22.8 shows the behavior of the policies under this workload. This workload, common in many applications, including important commercial applications such as database, represent a worst case for both LRU and FIFO. This So this looping actually is common. So looping of pages is common for database because they access the same pages all the time. It represents a worst case for both LRU and FIFO. So for this type of workload, kind of like in DSA, we have a best case, worst case, and average case. So this type of workload represent the worst case for LRU and FIFO. However, for algorithm, it's different. Kind of like in a stock property of LRU, since LRU has last in and first out, it is better for what you call this, the Adebali. I forgot that, but I mentioned that earlier. Yeah, Beladi's anomaly. So FIFO was not good at that because even with larger cache, it still performed poorly. Well, LRU does work well. So this algorithm LRU really fits for our modern cache-based CPU system, which makes the computation faster. But in this case, LRU and FIFO is in its worst case. The algorithm under a looping sequential workload kick out older pages. Unfortunately, due to the looping nature of the workload, these older pages are going to be accessed sooner than the pages that policies prefer to keep in cache. So what that does mean, so due to the looping nature of the workload, the older pages are going to be accessed sooner than the pages that the policies prefer to keep in cache. So though we have policies that make better use of our cache, it will be accessed or the older pages are going to be accessed sooner. Then we optimize that in cache. Indeed, even with the cache size of 49, a looping sequential workload of 50 pages results in 0% hit rate for LRU. Yeah. So interestingly, random fares notably better, not quite approaching optimal, but at least achieving a non-zero hit rate. Turns out the random has some nice properties. One such property is not having weird corner case behavior. So implementing historical algorithm. So this is the answer on how we actually implement this theory. To implement it perfectly, we need to do a lot of work, specifically upon each page access, like memory access, whether an instruction fetch or load or a load or store, we must update some data structure to move this page to the front of the list, like the MRU side. So to do this successfully, we need to activate some hardware capabilities or a data structure that keeps track of the page that we already access, or update some data structure to move the page to the front of the list, like the most recently used side. Contrast this to FIFO, where FIFO list of pages is only accessed when a page is evicted. By removing the first in page or when a new page is added to the list, to the last inside, to keep track of which pages have been listed and most recently used, the system has to do some accounting work on every memory references. So again, most recently used and which is the least recently used. Those are the parameters that is important. What are the pages that least recently used, so we know what to kick out. Most recently used, which are the pages are frequently used, so we know what not to kick out. The system has to do some accounting work on every memory references. Clearly, without great care, such accounting could greatly reduce performance. So we intend to reduce performance, but because of this increasing complexity, bad implementation or inaccurate judgment or guesses or decision, it could make it worse. So one method that could help speed this up is to add a little bit of hardware support. For example, a machine could update on each page access a time field in memory. For example, this could be in the per process page table. Per process, we discussed that in the previous video, or just in some separate array in memory, or just in a separate running array or in memory with one entry for physical page of the system. So that's the key. It must have that one entry for each physical page of the system, so that we can track each pages. So a time field again in memory. Thus, when a page is accessed, the time field would be set by hardware to the current time. So once we access that, the hardware would set it on the current time and mark it as already accessed. So then, when replacing a page, the OS could simply scan all the time fields in the system to find the least recently used page. So the way we do that is again time. That's how do you know when the page was accessed. Unfortunately, as the number of pages in a system grows, scanning a huge array of times just to find the absolute least recently used page is prohibitively expensive. So again, without great care, we can mess this up. So we need to create, imagine a modern machine with 4 gig of memory chopped into 4 kilobytes pages. This machine has a million pages, and thus finding LRU page will take a long time, even at modern CPU speeds, which beg the question, again, with policies and mechanism knowledge, do we really need to find the absolute oldest page to replace? Can we instead survive with an approximation? How to implement an LRU replacement policy? Given that it will be expensive to implement perfect LRU, can we approximate in some way and still obtain the desired behavior? Approximating LRU. As it turns out, the answer is yes. Approximating LRU is more feasible from a computational overhead standpoint, and indeed it is what many modern systems do. So instead of like scanning everything, we just need to approximate, and that's what actually how modern systems works. The idea requires some hardware support in the form of a use bit, which already existed in the hardware, sometimes called the reference bit, the first of which was implemented in the first system with paging, the Atlas one-level store. So the first bit actually again came from the classic, which is the Atlas. There is one use bit per page of the system, and the use bits lives in memory somewhere. So again, it can be any data structure, right? But this use bit lives in memory somewhere. They could be in per process page table, for example, or in just array somewhere. So again, per process page table. So remember, each process has a page table, right? That provides their allocation. It could be there or in just array somewhere, as long as it is in the memory, live in memory, where whenever a page is referenced, like read or written, the use bit is set by hardware to 1. The hardware never clears the bit though, i.e. sets it to 0. That is the responsibility of the OS. So the hardware never clears it to 0 or change it to 0. It is the responsibility of the OS. So the question, how does the OS employ the use bit to approximate LRU? Well, there could be a lot of ways, but with the clock algorithm, one simple approach was suggested. Imagine all the pages of the system arranged in a circular list. So how do we solve that approximation problem or avoid scanning all the pages? So there comes the clock algorithm. So imagine all the pages of the system arranged in a circular list. A clock hand points to some particular page to begin with. When a replacement must occur, the OS checks if the currently pointed to page P has a use bit of 1 or 0. Because if it has a use bit 1, therefore it's not a good candidate for eviction, right? Because it's most recently used. If or has been accessed, at least has been accessed. If 1, this implies that the page was recently used and thus is not a good candidate for replacement. Thus, the use bit for P is set to 0, cleared. So therefore, there we have a P for this algorithm of clock that will be set to 0. And there we go, finding a used bit or unused bit again. And the clock hand is incremented to the next page, which is P plus 1. So you may think that we goes about it randomly, but we actually points or increment to the next page. The algorithm continues until it finds a used bit that is set to 0, implying this page has not been recently used, or in the worst case that all pages have been, and that we now search through the entire of pages, clearing all the bits. So if we didn't get it, of course we will need to go to the worst case scenario, but at least we have an option now to not go or scan everything every time. So this is what the algorithm. Later we will add another features to it to provide the solution to this edge case. So the algorithm continues until it finds the use bit, implying this page has not been recently used. Note that this approach is not the only way to employ use bit to approximate LRU. Indeed, any approach which periodically clears the bits and differentiates between which pages have used bits of 1 versus 0. So any approach that periodically, okay, so like systematically or intervally that have used bits of 1 versus 0 to decide which to replace would be fine, because this is the key, the 0 and 1. So the clock algorithm of Corbatus was just one early approach which met with some success and had the nice property of not repeatedly scanning through all of the memory looking for unused pages. So these are the cache sizes blocks. So as you move further, as you get it bigger, LRU approaches the optimal, the FIFO not so compared to LRU. The clock, as you can see, it removes the, it doesn't perform as LRU, but it doesn't scan it either. So it's a good trade-off. So the behavior of clock algorithm variant as shown in figure 22.9. This variant randomly scans pages when doing a replacement. When it encounters a page with the reference bit set to 1, it clears the bit, sets it to 0. When it finds a page with the reference bit set to 0, chooses it as its victim. As you can see, although it doesn't do quite well as perfect LRU, it does better than approaches that don't consider history at all. Now, to solve that, we consider the dirty pages. One small modification to the clock algorithm originally suggested by Corbato that is commonly made is the additional consideration whether a page has been modified or not while in memory. Because if it's modified, therefore you likely don't want that to evict, because then you have to actually write that to the disk, otherwise the data will be lost forever. The reason for this, if a page has been modified and is thus dirty, it must be written back to disk to evict it, which is expensive. If it has not been modified and is thus clean, the eviction is free. The physical frame can simply be reused for other purposes without additional I/O. Thus, some VM systems prefer to evict clean pages over dirty pages. So clean pages are those bits that is unused but also not modified. To support this behavior, the hardware should include a modified bit, aka dirty bit. This bit is set anytime a page is written and thus can be incorporated into the page replacement algorithm. So anytime a page is written, it will be modified. Notice not read, because you don't really modify it when you read it. This clock algorithm, for example, so basically a write or written operation is much more important when it comes to considering the 30 pages, or with clock algorithm or with the LRU algorithm because it doesn't evict it as much as the clean pages. So the clock algorithm, for example, could be changed to scan for pages that are both unused and clean to evict first, failing to find those, then for unused pages that are dirty, and so forth. Other VM policies. Page replacement is not only policy the VM subsystem employs, though it may be the most important. For example, the OS also decide when to bring a page into memory. So aside from replacement, there's also a policy on where to bring a page into memory. This policy sometimes now called the page selection policy, as it was called by Denning, present the OS with some different options. For most pages, the OS simply use demand paging, which means the OS brings the page into memory when it is accessed on demand, as it were. Of course, the OS could guess that the page is about to be used and thus bring it ahead of time, kind of like a prefetch. This behavior is known as prefetching and should only be done when there's a reasonable chance of success. For example, some systems will assume that if a code page P is brought into memory, that code page P plus 1 will likely soon be accessed and thus should be brought into memory too. So they use this, the spatial location again. And again, fetching is like loading, right? Here, we're trying to get it in advance or prefetch the memory in advance, like the P plus 1 when we already have that P in the memory. Another policy, so that's the policy when to bring a page into memory, not the replacement or when we need to page fault or like when the memory is full, but when the memory is not full and we don't need replacement. Okay, so this is another policy in VM subsystems. Again, for most pages, the OS simply uses demand paging, which means the OS brings the page into memory when it accesses on demand, as it were. Of course, the OS could guess that the page is about, but for most pages, actually, it only accesses the pages or put the pages from disk to memory as the memory demands it, or when the replacement code occurs, like when you need to swap something or when you run a program from disk. So how do you determine that? So these are the policies that dictates that, such as the P plus 1, again, the locality, because again, we're trying to optimize the cache. That's why your program runs so fast, is because the OS or VM subsystem has that policy. When you access 1 P, it also accesses P plus 1 too, because it exhibits spatial locality. So kind of like in about phase where most of the functions we use will probably be used again, so they put that at the front. Another policy determines how the OS write pages out to disk. So another policy that VM subsystem needs to know is how do it actually write the disk. Of course, they could simply be written out one at a time. However, many systems instead collect a number of pending writes together in memory and write them to disk in one more efficient write. So many VM subsystem actually put that in one side of memory and then write them into the disk in one efficient write, because again, writing one by one on disk is less efficient. This behavior is usually called clustering or simply grouping of writes, and is effective because of the nature of disk drives, which performs a single large write more efficiently than many small ones. Trashing. So this is the last concept when it comes to VM subsystem policies. Before closing, we address one final question. What should the OS do when memory is simply oversubscribed? So we discuss the replacement or page fault, but what if it's oversubscribed for a long period of time? So, and then we have to fault to the disk every time and use our replacement policy code. And the memory demands of the set of running processes simply exceeds the available physical memory. In this case, the system will constantly be paging, a condition sometimes referred to as trashing. So that's where your memory and CPU, gets hot and gets thrown out the real trash. Some earlier operating system had a fairly sophisticated set of mechanisms to both detect and cope with trashing when it took place. For example, given a set of processes, a system could decide not to run a subset of processes, with the hope that the reduced set of processes, working sets, the pages that they are using actively fit in memory and thus can make progress. So they decide not to run a set of processes that you want to get out from disk, therefore only run that actively processes in memory. This approach is generally known as admission control. States that it is sometimes better to do less work, which is actually well, than try to do everything at once poorly. A situation we often encounter in life as well as in modern compute systems. Some current systems take more draconian approach to memory overload. For example, some versions of Linux run out of memory killer. When memory is oversubscribed, this daemon chooses a memory-intensive process and scales it. So this actually kills the actively running process, which is the largest memory. But there's a downside to it. Thus, it reduces memory in a more subtle manner. While successful at reducing memory pressure, this approach can have problems. If, for example, it kills the X server and thus renders any application requiring the display unusable. So sometimes it can kill the display because those processes are usually the memory consuming process. So we have seen the introduction of a number of page replacement and other policies which are part of the VM subsystem of all modern operating systems. Modern systems add more some tweaks to straightforward LRU approximations like clock. For example, scan resistance is an important part of many algorithms such as ARC. Scan resistant algorithms are usually LRU-like, but also try to avoid the worst case behavior of LRU, which we saw with the looping sequential workload. Thus, evolution of page replacement algorithm continues. So scan, again resistant, so it checked if it's modified, right? So it is an improvement with the clock. For many years, the importance of replacement algorithms had decreased as the discrepancy between memory access and disk access times were so large, specifically because paging to disk was so expensive. The cost of frequent paging was prohibitive. Simply put, no matter how good your replacement algorithm was, if you were performing frequent replacements, your system became unbearably slow. Thus, the best solution was simple. if intellectually unsatisfying one. Buy more memory. However, again, recent innovations in much faster storage devices like SSDs have changed these performance ratios yet again, leading to a renaissance in page replacement algorithms. So because we have fast SSD today, it's not as slow as the hard disk drive before. Uh, a development of algorithm for this page replacement, you know, is important again because those small transfer pages really matters because the system just not so you can see now I'm using 39% of memory, but if I am using SSD, I can easily get that program from my SSD compared to my hardware or hard disk if I'm using a hard disk drive. VAX. So that's the reason why SSD are faster when you're using changing to SSD make your system faster because you're actually accessing it on that part of memory, and a page better page algorithm that works in memory actually makes it efficient. So, complete virtual memory system. So, we've seen key elements of such systems including numerous page table designs, interaction with TLB, sometimes even handled by the OS itself, and strategies for deciding which pages to keep in memory and which to kick out. However, there are many other features that comprise a complete virtual memory system, including numerous features for performance, functionality, and security. So we have discussed the vocabulary. Now we will now see it in a more holistic and real-world application. So crooks, how to build a complete VM system. What features are needed to realize a complete virtual memory system? How do they improve performance, increase security, or otherwise improve system? VAX or VMS Virtual Memory System. The VAX 11 mini computer architecture was introduced in the late 1970s by Digital Equipment Corporation. DEC was a massive player in the computer industry during the era of mini computer. Unfortunately, a series of bad decisions and the advent of the PC slowly but surely led to their demise. The architecture was realized in a number of implementation, including the VAX 11/780 and less powerful VAX 11/750. The OS for the system was known as VAX or VMS or just plain VMS. One of whose primary architects was Dave Cutler, who later led the effort to develop Microsoft's Windows NT. So this Dave Cutler actually is a terrific or enormous system thinker that leads to the creation of one of great OS that powers the world, which is the Windows. So they developed it. He came from VAX, which unfortunately was demised, but we will learn a lot from it because it's STEM. It's easy to understand. It is where the basic of virtual memory, even today, all the principles we learned from that uh, is applied today. Um, VMS had the general problem that it would be run on a broad range of machines, including very inexpensive Voxen, yes, that is proper plural, two extremely high-end and powerful machines in the same architecture family. So again, it started with a question on how to actually run that in multiple devices, to kind of like serve a lot of customer, which smart engineer or talented engineer has been able to solve. Thus, the OS had to have mechanisms and policies that work and work well across the huge range of systems. So we will discuss memory management hardware, a real address space in real world, page replacement, how does it actually work in the background. So page replacement, the reason why we have an entire chapter for that, because we will see how that uh, the implementation of that pages. We started with base or bound register to segments, which led us to pages, and now we're going to actual page replacement that work in the real world because it came from years or decades of research. So other neat tricks, the Linux virtual memory system. So the Linux address space, again we'll start with the address space, how it converts to bytes, etc. Page table structure, so the page table structure still in here, which we discussed in the previous video in detail. Large page support, the page cache, so we still tackle the large page support, the page cache or the cache to make it faster. Security and buffer overflow, so that's where we did discuss the spectacle and other smart or code that overwritten the entire system. Other security problems, meltdown and spectre.